Right. So this is another nice question. Which of the following statement is false with regard to activation energy of a reaction? The activation energy of the forward reaction in an exothermic process is lower than that of an backward reaction. So we will draw a exothermic reaction. Okay. So you know, in an exothermic reaction, the delta G is negative. So that is why I drew the products a little bit lower than the reactants. So this is the activation energy of the forward reaction. Okay. And this is the activation energy of the backward reaction. So what they are telling, the activation energy of the forward reaction is lower than the activation energy of a backward reaction. In fact, this statement is correct. The activation energy of a slow reaction is less than that of a fast reaction. So what can you tell about this one? Slow reaction and a fast reaction. So we cannot exactly predict. Now, normally when you have a slow reaction, yes, it is true that activation energy should be very high. Okay. And when you have a fast reaction, the activation energy should be very slow. Okay. Very small, in fact. But this is okay when you have like a direct elementary reaction, one-step reaction. Okay. But when you have multiple reactions, like multiple steps, and there can be some steps where the activation energy is low, one step where activation energy is high. Okay. And the rate is determined by the slowest step at that case. Okay. But with this statement, that they have given, the activation energy of a slow reaction is less. That is totally first point is wrong. But if it is given, the activation energy of a slow reaction is high. Let's say this is given as high. Okay. Than that of a fast reaction. So this is in general, it is okay if this is given as high. But in fact, it should be also considered only for elementary, because when you have multi-step reaction, still you need to have to consider about a step that is slowest to identify the rate. That is depending on the rate. But there can be some steps where the activation energy is lower and some step the activation energy is high. But overall, if there is high here, that is correct. Okay. So the activation energy of a slow reaction is less, means this is totally wrong. The activation energy of a given reaction pathway is unaffected by a catalyst. In fact, this is correct. C is correct or wrong? What do you think? What is your opinion on C? I will read the last one also. Higher the initial concentration of the reactants, lower the activation energy. So activation energy is depending upon the mechanism of a certain reaction. Whether you change the concentration or whether you change the pressure or anything, this won't change. Activation energy is depending upon a certain type of mechanism, not concentration or anything. Okay. What do you think about C? The activation energy of a given reaction pathway is unaffected by a catalyst. What do you think about that? Is that correct or wrong? I am telling it is true. Can you tell me why? Okay, so I have one answer saying true. Yes, it is true. It should be true. So why it is true? Because normally we say we add a catalyst to reduce the activation energy. So someone might think, okay, it reduces the activation energy, mean it should have an effect to the activation energy of the reaction. What about others? Yeah, you're correct. So Kimithu, you are correct. The idea is you have a certain activation energy. Okay, so the catalyst provide pathway with lower energy but does not affect the pathway. Yeah, that's the truth. The idea is catalyst, what it does is it gives an alternative pathway. That is the term. Because there can be a pathway where with a higher activation energy, but what catalysts do is a different mechanism. That is why it has a different path. It has a different mechanism. For an example, you have like A reacting with B and forming C. Okay, then you have this your catalyst D. So what the catalyst do is here it will first react with D and will let's say produce X plus C. Okay, and this X might react with B, again producing D for an example. So the overall reaction is A plus B giving C. Okay, so this is one mechanism where A directly react with B to form C. But when you have a catalyst, it goes with a different mechanism. So A plus B is like this, A plus B giving C. Okay, but when you have this catalyst, now the mechanism is slightly changed. You can imagine it goes like this. In fact, it could be like this. Okay, but there are two hypes. One is A plus D forming the intermediate X plus your product C. And this could be again going to X plus B. For an example here, when you have B, that will react with X to form D. For an example, this is not a real reaction, just to understand. So this is two-step mechanism. This is one-step mechanism. So one-step mechanism, you have a higher energy, activation energy. Here, this is very small. And here, this is also very small. So when you add these two, or one of these two steps always will be lower than this. In fact, the two steps should be lower than this. For an example, if the uncatalyzed energy is 100 joules, okay, if this is 100 joules, and this one also, let's say 100, and this is, let's say 20. Okay, now this is not a good catalyst. This is very bad catalyst, because without the catalyst, you have 100 and it is happening when you give the 100 kilojoule energy. But even with the catalyst, if you have to like provide 100 kilojoule, there is no point of using this catalyst. Okay, so try to understand this. C is correct here. So A and C is correct. So basically the answer is 5. Okay, these are very important determinations.